Welcome back. In this video, we began our study of sequences and series. Now, series are based on sequences. So sequences are what we study in order to get to series. And series are a very important part of computational mathematics. In fact, there are many, many applications from biology to medicine to chemistry to engineering that need series in order to find the values of things. In fact, much of what our computers are based on started with studies of different kinds of series. So what exactly is a series? Well, we can't get to the series until we talk about the sequence. Now, what is a sequence? When we start with the definition of a sequence, we can talk about an infinite sequence or we can talk about a finite sequence. But a sequence is basically an ordered list of values separated by commas. And ordered means that there's a particular order. So there's a first value, a second value, a third value. We write them as a sub 1, a sub 2, a sub 3, a sub n forever, where the subscript is tracking which one it is in the list. Now, I've started this list with the subscript 1, but I don't have to. I could start with the subscript 0 or I could start with the subscript 5. We do typically use either the counting numbers or the whole numbers or some subset of those. We don't use negative numbers for the subscripts of sequences. So a sequence is just an ordered list. It's not a set because a set doesn't have any order. All the values are jumbled up. A sequence is an ordered list. So we know which one comes first, which is second, which is third. There's an order to it. Now, they could be finite, as in we could go from A1, A2, A3 and stop. That's an ordered list of 3 different terms. Now, the values themselves don't have to be numbers, but in mathematics, we're primarily concerned with sequences of numbers, specifically sequences of real numbers. So when we're looking at these, what we're going to be focused on are sequences of real numbers. Now, we're not going to look too often at finite sequences because what we're mostly concerned with, of course, are infinite sequences. And we want to examine what happens to the sequence as it goes forever and ever. Is there a pattern? Can we predict what the next one in the list is going to be? Can we predict some value that the sequence approaches as n approaches infinity? This is basically what we want to study with a sequence. Now, I said that the most important construct in this particular unit for this chapter and the next is what's called a series. So what's a series? Well, series is based on a sequence. A series takes the terms of a sequence, an ordered list with commas in between, and it adds them up. So it's the sum of the terms of a sequence. So a series is just take the commas out and put plus signs in its place. So that's what a series is. And a series is what we're mostly concerned with in chapters 5 and 6. But in section 5.1, we're only going to be looking at what a sequence is. So let's go ahead and form a definition that will help us to talk about sequences. We want to start with the definition of a term or an element. A term is what we refer to one individual value in the list. We call it a term, or you can also call it an element. The symbol n, which is what we're tracking with these subscripts here, is called the index or the index of the sequence. So it tracks which order it's in, which one it is in the ordered list. Each particular term has a specific order, notated by using the index. So a sub 5, if I start with a equal 1, would be the 5th in the index. Now, you do have to be careful because we can have a sequence that starts at something other than 1. For example, I could have a sequence which is A0, A1, A2, A3, and so on. Now, in this particular sequence, the first one is a sub 0, and the second one is a sub 1. So the order doesn't necessarily match the subscript. So keep in mind that there's an order position and a subscript, which is the index, but they do go one after the other. So if this is 2, the next one will be a sub 3, and the one after that will be a sub 4. So once we have the starting place, then they increase by 1 each time. But again, it doesn't necessarily have to start at 1. It could start at a sub 0. We could even, if we wanted to, call one b sub 5, b sub 6, b sub 7, b sub 8, and so on. Now, you'll find that there are good reasons for starting at 0, and there are some good reasons for starting at 1. There aren't good reasons for starting at 5. So most of the time, our sequences will either start with a subscript of 1, or they'll start with a subscript of 0. Now, these are infinite sequences, and we have another notation to show that, which is using the curved bracket, a sub n, and we typically name them a sub n, b sub n, or c sub n. So a, b, or c with a subscript of n, and it goes from n equal 1 to infinity. Or you could have this one, for example, right here. This is equal to the sequence a sub n, where n goes from 0 to infinity. You can also drop what the value of the subscripts is if it's clear from your situation. If it's not clear, you should go ahead and list them on the right side, almost as you would in the fundamental theorem of calculus. Now, this one down here can also be written in a combined form inside the curved brackets, b sub n equal 5 to infinity. Again, once they have the starting subscript value, they go by ones from that point on. Now, we define or can define a sequence as a function where the domain is some set of positive integers. Could be the counting numbers, as we saw right here, could be a subset of the counting numbers from 5 to infinity, or we could use the whole numbers from 0 to infinity. There's no mathematical reason that we can't use negative numbers. It's just our habit in mathematics not to do that. So the lowest value we'll use for a subscript will be the 0th one. Now, if we do this, we're defining a function where the domain is the value, basically, of the index, the subscript, and the range is the particular value in that position. So the domain are all the subscripts that you've used, in this case, 1 to infinity, going by integer values. In this case, 5 to infinity by integer values. And in this case, 0 to infinity by integer values. And the y values, or the function values, are the particular numbers that show up in the list itself. So when we think of it as a function like this, we can then plot the function onto a graph, and we can see what behavior that particular sequence has. Note that all sequences are going to be discontinuous everywhere because they only exist at integer values of the subscript. So we don't have any 1.5 or 1.7. So it consists of discrete dots or discrete points on the graph with space in between each of the points. So they're never continuous. They're always discontinuous everywhere. And because differentiable functions have to be continuous, if it's never continuous, then it's never differentiable. So sequences are not differentiable functions. They are functions. They do pass the vertical line test. They're just not connected. They're not continuous. This first one on the left is the sequence n plus 1 divided by n squared from n equal 1 to infinity. And you'll see this dot up here that has been plotted for n equal 1. So that would give us 1 plus 1, which is 2, divided by 1 squared, which would give us the value of 1 comma 2. So when n is 1, the y value is 2. So that gives us this ordered pair right here. And that's on the graph of the function, which represents the sequence. And then we can allow n to be 2. And when n is 2, we get 3 in the numerator and 2 squared is 4, so we get 3/4. So when n is 2, we have the y value of 3/4. So we can plot these, and if you look at this graph, you can tell very quickly, you can predict that as n goes to infinity, the value of the sequence is approaching 0 because clearly the graph of the function is decreasing for all values of n and approaching the x-axis. This makes sense because if we were to take the limit of this representation of the sequence, we know that n squared being degree 2 overpowers the numerator of degree 1 and drives it towards 0. Now, if we look at the graph on the right, this is the graph of the sequence a sub n equal to n divided by n plus 1. And you'll notice that it also has discrete dots represented by the dots in red. Now, next to it, in black, we have the function x divided by x plus 1. Notice that the graph of the function f of x is a continuous function. It has values at all the points in between the integers, so it's continuous and connected. But the sequence itself, the red dots, is not connected. Notice that the sequence is following the function and doing what the function does. This does not always happen. Sequences do not always behave the way the function does. Sometimes they do, sometimes they don't, and we'll have to look at when that happens and what makes it happen. In this case, as x goes to positive infinity, the function is approaching the horizontal asymptote y equal 1. And because the sequence is following what the function does, the sequence is also approaching the value y equal 1. So we could predict that the further out we get, the closer the sequence gets to the value of 1. Now, if we want to list some of the values on the sequence for either one of these, then we'd have to compute some more. So basically, for the one on the left, I have 2 for the first value, 3/4 for the second value. And for the next one, remember, this is a sub 1. This is a sub 2. Now I need a sub 3, where the subscript is 3. 3 plus 1 is 4 over 3 squared, which is 9. So I get 4/9 for the next one. And then I have a sub 4, which would give me 5 over 16. Right? Now, is there a pattern to this? Can we predict the pattern based on what we see now in this list of numbers? Well, it looks like the numerator is going 2, 3, 4, 5. I would predict that the next one is going to be a 6. That's my prediction, which I'll put in red because I don't know for sure if it's right. Now, I can't tell based on the first one what the pattern of the denominators is. But if I look at the second, third, and fourth, it looks like 2 squared, 3 squared, 4 squared, that would be 5 squared. 5 squared would give me 25. Does that work moving backwards for the first one? 5 squared, 4 squared, 3 squared, 2 squared. Yes, 1 squared would give me 1, which would just give me 2. So the pattern does work for the first. This is something that we'll need to be able to do with sequences to predict the pattern. So based on the numbers, we can predict the pattern. And also based on this explicit formula, we can predict the pattern. And again, this is a sequence that goes forever. And we said that the limit of this as n goes to infinity is probably 0 because that's what it looks like the values are approaching. This one on the right is different. Let's write down some of the values of the one on the right. The one on the right is n divided by n plus 1, starting with n equal 1, which would be this first red dot here. So that would give us 1 over 2, or 1/2. So when n equal 1, we get 1/2, which makes sense. Now, when n equals 2, we have 2 over 3, which is 2/3. When n equals 3, we have 3 over 4. And when n equals 4, we have 4 over 5. Let's write down this list of numbers. The first sequence value is 1/2. The second was 2/3. The third was 3/4. And the fourth was 4/5. And again, this corresponds to a sub 1, a sub 2, a sub 3, and a sub 4. Again, assuming that the sequence starts at 1 and goes to infinity. If we look at this pattern, can we predict what the next one would be? Well, it looks like the numerators are going increasing by 1, and so are the denominators, but starting at a different value. So it looks to me like the next value in the list should be 5/6, and in fact, that is what it is. And then I can take the limit of this sequence by looking at either representation of it, the graph, the formula, explicit, or the list of numbers, and I can predict that the value as n goes to infinity is going to approach 1. It never gets to 1, but it gets arbitrarily close as you want it to be. So these are some of the things that we have to consider when we're looking at sequences. There is a function on Desmos that will let you explore different sequences, one that I've created with some explanations of what each part does, which is this one right here. So let's take a look at this one. I'll leave it on the screen long enough, and let me share my screen with you so that you can see a little bit closer what I'm doing. I can get it to share. There we go. Now it's sharing the screen. So take a look at that. Type that in, www.desmos.com/calculator/TBLOYX9WMY. And let's take a look at what this one looks like. If you have my notes, Control click will do it. So here is an example of a set function on a Desmos calculator that will let you see what the behavior of the graph is. So you can notice how the sequence a sub n behaves for increasing values of n. Adjust uppercase n to take more points of the sequence. So coming down here on the left, I'll see that there is a slider bar for uppercase n, which is right here. If I increase the number of dots, that increases the value of uppercase n. Now, the formula will only accept values in terms of x. Normally, this should be a of n is equal to n over n plus 1. Because of the way Desmos works, we have to enter x instead of n. It thinks n is a slider and it messes everything up. So we graph, in essence, the function a sub x equal x over x plus 1. And then we tell it to plot all the points n and a sub n in red. Now, if you don't want it to plot in red, you can highlight that and you can make it a different color. And for those of you who are colorblind, it might be better if I change this now to blue so that you can see it a little better. And this will plot points, right? And you can plot them as points, circles, or X's. I prefer the dots, right? The next command basically here is telling it that lowercase n is a list of values from 1 to uppercase n. In other words, it's a list, an ordered list of numbers. It's the domain of our sequence. And we're going to start from 1. So this goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we could start it at a different value, 5 to infinity or 0 to infinity, as long as the sequence is defined for those values. Now we have the slider bar down below, which sets the number of dots that you see there. And that's basically what you have in this particular graph. Now, if you're looking at this one right here, this is what the sequence looks like. If you highlight that circle and you turn it on, it will graph the function, which you can see here as a dashed line. And you can tell that on this particular one, the sequence, which is the discrete dots, is following the pattern of the function, which is represented with x. And you can predict that as n goes to infinity, the sequence of discrete discontinuous blue dots is approaching the value y equal 1, which must mean that as we go to infinity, the value of the sequence x over x plus 1 must be approaching 1, or n over n plus 1. Let's now go back to our notes. Again, we typically use lowercase a, b, and c for the names of sequences. We'll often have an a sub n and a b sub n. Not as often, we might have a c sub n or even a d sub n, but that's pretty rare. The subscripts tell us where the ordered list begins. Most of the time, it will begin with 0 or 1. There are some excellent reasons when we get to geometric series, adding up the terms of a sequence, to start at 0. Why start at 0? The short answer is it makes our formula simpler. So anything to make the formula simpler is a good thing. Starting at 0 does make some of the formulas simpler. Does that mean you can start at 1? Yes, but the formulas will be slightly more complicated. Now, let's talk about what happens when we're talking about an arbitrary term in the sequence. If we don't want to talk about the first one, the second one, the third one, or any particular value, we just want to talk about an arbitrary one, we tend to call it a sub n. So we call it a sub n, which is what you see right here. And then in order to know what's immediately in front of it and what's immediately after it, we need to be able to write them in order. But remember, once the subscripts start, they proceed by ones from one to the next to the next to the next, which means if this one's a sub n, the one after it is a sub n plus 1, and the one after that is a sub n plus 2. What would come next? Well, what would come next would be a sub n plus 3, and then a sub n plus 4, and then a sub n plus 5, and so on. Now, what about in front of the a sub n? Well, the one right in front of it is 1 less than n, so it's a sub n minus 1. And the one in front of that would be a sub n minus 2. And in front of that, we must have a sub n minus 3. And in front of that, we have a sub n minus 4, and it continues in that pattern towards the left. Now what we want to do is we want to take a look at some sequences and we want to predict what the patterns are. We've already done this up above when we were looking at the graphs, and we wrote out several of the points, and then we represented the sequence by an ordered list of the y values of each point. And then we predicted what the next term in the sequence would be by looking at that list of y values. Often when we're doing this, we do ignore the first term like we did in one of the ones up above and find a pattern for the later terms. Then we backtrack to make sure that the pattern does match for the first term as well. If it doesn't match for the first term, it's not the right pattern. So let's take a look now at example 1. When we look at the sequence that is in example 1, we can see that the first term is 2, which is a whole number. It doesn't match the pattern of the other terms in the sequence because they're all proper fractions. The denominators are larger than the numerator. So we're going to ignore the first term for a minute, and we're going to focus on the later ones. We're going to see if there are a pattern that predicts what we have here. Now we have to decide where we want to start n because that will affect the formula. So we're going to make the assumption that n starts with 1. So we have the sequence from 1 to infinity. And that's going to be with this list of numbers here. So that means that a sub 1 is 2. And that means that a sub 2 is 3 over 4. And a sub 3 is 4 over 9. Now we want to use the subscript n and manipulate it somehow to see if we can come up with an explicit formula for it. It looks to me like the numerator is going to be the subscript plus one more value. Does that work for all of them? Well, let's see. A sub 4 is equal to 5 over 16. It works for that one. And A sub 5 is equal to 6 over 25. It works for that one. So it looks like it works for the second, third, fourth, and fifth, the only ones that we can see. Does it also work for the first one? A sub 1 is 2. Yes, 1 plus 1 would give me 2. So that looks like I can take the subscript n and add 1 to it to get the numerator. So this is going to give me n plus 1 in the numerator. Now, what about the denominator? Looking at the denominator, it looks like I take the subscript and square it. That works for the second, the third, the fourth, and the fifth. Does it work for the first one? Let's backtrack. Yes, it does, because 1 squared would give me 1. So this is 1 squared. So it does work for the first one, and this gives me a pattern. This gives me n plus 1 over n squared, proceeding from n equal 1 to infinity. Now, if I had chosen n equals 0 to be the first one, then the numerators would not be n plus 1. If this were an A0, to get a 2, I would have to add 2 instead. And instead of this being n squared, it would be n plus 1 quantity squared. So the formula depends upon where you start the particular sequence. It does make a difference. Let's rewrite the same formula, but using instead a sequence which starts at 0. So we're going to let b sub n from n equals 0 to infinity be the same list of numbers: 2, 3/4, I'm spreading them out, 4 over 9, 5 over 16, 6 over 25, and so on. And we're starting with n equals 0. If we start with n equals 0, again, this is a sub 0 right here. To get the numerator, I need to add 2 to the subscript. So this looks like the numerator would instead be n plus 2. Does that work for each of them? Yes, in fact, it does. If I add 2 to the subscript, I would get the value in the numerator. How about the value in the denominator? If this is a sub 1, that's not related directly to the 1, but it is related to 2, which is 1 bigger than 1. So if I take the subscript and add 1 to it and then square it, I should be able to come up with this sequence of numbers in the denominator. In other words, I have to add 1 to the subscript and then square the subscript to get the same numbers in the denominator. This then becomes the explicit formula if we start at n equals 0 and go to infinity. It generates exactly the same list of numbers as the explicit formula in blue. They both generate the sequence 2, 3/4, 4/9, 5/16, and 6/25, and so on. In other words, the explicit formulas are not unique. If I wanted to start at 2, you're right, I would again have a different explicit formula. They're equivalent, though, in that they all produce the same ordered list of numbers. Now, there's another way of writing down sequences rather than explicitly, and that's called using what's called a recursive formula. Recursive means, well, cursive means curving around, and means again. So curving around again, coming back again to what you had before. In order to use a recursive formula, the following term is based on one or more of the ones in front of it. In other words, I can't know what the fifth one is unless I know what the fourth one, third one, second one, and first one are. To know the fifth, I have to know the string of list of terms up to the fifth one: the first, the second, the third, the fourth, whether the subscript starts at 1, at 0, or at 5. first, second, third, fourth, and fifth still tracks which order they are in the ordered list or the sequence. So recursive formula defines it in terms of what comes in front. And the most famous recursive sequence is the Fibonacci sequence. We call it the Fibonacci sequence, but really there are hundreds of Fibonacci sequences. Fibonacci was an Italian mathematician. He was fascinated with sequences, and he studied many, many of them. Now, this one in particular has lots of applications in biology. Believe it or not, if you look at the pieces of a pine cone, they swirl around in a pattern according to this list of numbers that you see here. If you look at the openings in a nautilus shell in the ocean, you'll also find that they follow the same pattern. The pattern of the pieces of pineapple form the same pattern as they go around. If you look at the seeds in a sunflower, they follow the same pattern. In fact, the petals on some flowers follow the same pattern. There's one leaf, then two leaves, then three leaves, and so on. It follows the same pattern called the Fibonacci sequence. Why that happens? Well, there are some theories, and the theory is that this leads to the most amount of sunlight for particular plants, or the most effective way of packing things into a dense space. But really, why this sequence? We don't know. It's part of the beauty and the mystery of mathematics. So this is a Fibonacci sequence. And when we look at this particular sequence right here, we want to know, is there a rule that gets us from the first to the second to the third? So take a look at this one and see how you can generate this list of numbers. What's the pattern? So take a moment and think about it. Do you have a beginning? If you've seen the Fibonacci sequence before, then you know what the pattern is. The pattern is take the first two numbers in the list, which are called the seed. These two right here are called the seed of the Fibonacci sequence because they determine the list of numbers that follow it. And the definition of the Fibonacci sequence is to take the two immediately in front, add them together, and that gives the next term in the sequence. So 1 plus 1 generates the 2. Then to get the 3, you take the two numbers in front of it, 1 plus 2, which gives you 3. To get the next value, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. This is recursive. In other words, I can't know the 34 without knowing all the ones in front of it. It's a recursive definition. So how do we write down this recursive definition? The recursive definition says a generic term in this sequence comes from adding the 1 in front of it, a sub n minus 1, to the 1 in front of that, a sub n minus 2. But notice that that is not enough. To get a particular sequence, you not only have to specify the rule, which is add the 2 in front to get the next one out, but you have to give the seed values. In this case, we would give seed values of A1 equal 1 and A2 equal 1. In other words, they're both 1. That generates the list of numbers, the ordered list, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. If I change the seed, I change the Fibonacci sequence. It's still a Fibonacci sequence. The rule is the same, but the list would look different. So let's see what happens. If I keep the rule the same, it's still a Fibonacci sequence, but I change the seed. A1 is still 1, but A2 is now 2. What does that do to the list? Well, that means that I would start with 1, and the second one would be 2. And then the next one would be 3. And then the next one would be 5. In other words, it would look like the one up above, but it would be missing this first term here. It would drop off one of the ones. let's suppose I made something totally different. And instead of something that was already in the sequence, I put in something that was not in the sequence to start with. In this case, A1 is 1 and A2 is 4. At this point, they're all going to veer off of the previous sequences. In this case, the next one would have to be 5. 1 plus 4 is 5. Then 4 plus 5 is 9. 5 plus 9 is 14. 9 plus 14 is 23. 23 and 14 is 37. 23 and 37 is 60. Then 97, and so on. It generates a Fibonacci sequence, but because the seed is different, the ordered list is different. But the pattern is the same. The pattern is this recursive relationship that the generic A sub n is equal to the sum of the two in front of it, A sub n minus 1 plus A sub n minus 2. Now, when we talk about sequences, we can have both an explicit formula and a recursive definition for some sequences. Some sequences can be written both ways. The Fibonacci sequence can only be written recursively. There's no explicit formula to write that one down. It doesn't exist. There's not one. You can try and find one, but you're never going to find it. There is no explicit formula for the Fibonacci sequence. But there are other sequences for which we can either write an explicit formula or a recursive. So which one do we want to use? Well, we typically want the explicit formula. What's the disadvantage to the recursive ones? Well, the disadvantage to the recursive ones is you have to know all the ones that preceded it to know the next one. So if I want A sub 99, then I have to know all the ones from 1 all the way up to 98. Or if I was starting at 0, from 0 up to 98. In other words, I couldn't get the 99th one without knowing the ones in front of it because it's based on what comes before. And you may say, but you only need 97 and 98. Yes, but to get 98, I have to have 97, 96. And to get 96, I have to have 95 and 94. Do you see how that works? So in other words, we've got to have all of them up to that one, which is a lot of work. An explicit formula, on the other hand, as we saw in some of the ones up above, you simply take the n equal 99 and you substitute it in the formula. So that's a huge advantage. Let's take a look at one of these formulas that we had. This is a formula right here, which is an explicit formula. I don't need to know all the ones between 1 and 98 in order to find the 99th. I just add n equal 99. I get 100 over 99 squared. It's exactly what that 99th one would look like. Now let's take a look at our next example, number 3. We want to find both an explicit formula and a recursive formula for the sequence 5, 8, 11, 14, 17, and 20. So there must be a formula that's both recursive and one that's not recursive. We're going to start using n equal 1 to infinity, and then we're going to redo the problem from n equals 0 to infinity. And we're going to compare and see how this changes the formula, and we're going to decide which one we think is easier. Now, how can I get from one of these to the next one? Is there some relationship between them? Looking at them, I can tell that I'm increasing by 3 each time. So a recursive definition then would basically say, so we're going to start with the recursive definition. And we're going from n equal 1 to infinity. Basically says that to get to the next one, take the 1 in front of it and add 3. Does that work? Yes. If I take 11 and add 3, I get 14. If I take 14 and add 3, I get 17. 17 add 3, I get 20. But again, this is a recursive definition. So I've also got to give the seed, which would be, in this case, the first one. A1 equal to 5. And that would generate that list of numbers. Start with 5, and then from there on, add 3 to get to the next. So this is a recursive definition, but it's a disadvantage to use it because I have to know all the ones in between to get to, say, the 20th one. So we want a way to write this explicitly if we can. And we can. What would the formula be here? Let's start with the subscripts, and let's write the subscripts below this. So we have A1, A2, A3, A4, A5, and A6. We want to find a formula involving the subscript that generates the value of that term. So it looks like A1 is 5 and A2 is 8. So basically I want to start with 5 and I want to add 3 one time. But to get from 5 to 11, I add 3 twice. And to get from 5 to 14, I add 3 times. So in other words, I'm adding 3 one time for each jump that I make. Notice that this adds 3 once, which is the subscript of the previous term. In other words, n minus 1. So it looks to me like a formula for a sub n would be to start at 5 and multiply by 3 n minus 1 times the subscript in front. So this would give me n minus 1 times 3 equal 5. Now, does it work for all of them? Well, let's check. I'm starting with a sub n at 1. 1 minus 1 would give me 0. So I wouldn't add 3 at all. I just get 5. That generates a sub 1. Then I let n be 2. 2 minus 1 is 1. So I add 3 one time, which brings me to 8. And then I let n be 3. 3 minus 1 is 2 times 3 is 6 plus 5 is 11. This will generate the list of numbers. Clearly, this is a formula which is explicit, which can be used to generate the same list of numbers, but doesn't require knowing the interim values. Now let's take a look at the same problem again, but let's now go from n equals 0 to infinity. This is slightly different. So we have 5 as a sub 0. We have 8 as a sub 1. We have 11 as a sub 2. And we have 14 as a sub 5, and so on. We'll write one more down. Oops, not 5. How'd I get 5? A sub 3, a sub 4, right? So when we're looking at these, what am I actually doing? Well, instead of starting at 1, I'm starting at 0. Can I apply the same idea? Well, yes. In this case, can I use the same recursive definition, the generic a sub n, recursive, start with the 1 in front, a sub n minus 1, and add 3. But instead of a0 being, or a1 being 5, a sub 0 equals 5. In other words, the first number is 5, and then after that, make sure you add 3 to get from 1 to the next to the next. This is the 0th, the first, the second, the third, the fourth, which means that's the first. Okay. It can be a little confusing when the subscripts don't follow the ordinal position, ordinal meaning order, first, second, third, fourth, and so on. We don't usually talk about a 0th, but we will be talking about a 0th in this class. This does work. This is a recursive definition, but starting with the subscript 0 instead of starting with the subscript of 1. How can we take this explicit formula here and rewrite it in some format so that we can generate the same list of numbers? So the non-recursive formula, the explicit formula, a sub n, if we start with 5, what do I want to do? Well, to get a1, I want to add 3 one time. And to get to a2, I want to add 3 twice. In other words, the number of times I add 3 matches the subscript now. So I can simply write that this is going to be 5 plus 3n, right? Or I could write it as A1 plus 3n. Or A sub 0, rather. And this formula over here in blue can be written as A sub n is equal to A1 plus 3 times n minus 1, where, of course, A1 is 5. So now we see that we have an explicit formula on the left and the right that correspond to starting with different subscript values. Which one do you think is easier? Now, in some ways, it was easier to come up with the explicit formula when we started at 0, which is one of the reasons we like to start at 0. The number of times we needed to add 3 corresponded with the subscript of that term. And this is one of the arguments for starting a sequence at n equals 0. The other one is the formula for a geometric series, which we'll see shortly. The example that we just saw is an example of something called an arithmetic sequence. Now, an arithmetic sequence is based on the formula for a line. And if you look at this formula that we see right here, this does look linear, doesn't it? A sub n is the y value, n is taking on the domain or the x value, and this looks like mx plus b. It looks like a line. And when it is that sort of sequence, we call it arithmetic. Now, these basically look like the line and slope intercept form, and this common difference between terms, add 3 each time, serves as the slope. So if we start at n equal 1, we have the formula a sub n is equal to a first plus d times n minus 1, where d is the difference between successive terms. If we start at 0, we can write a sub n is equal to a sub 0 plus d times n, or n times d, whichever way you want to write it, right? So hopefully this makes sense to you. Now, arithmetic sequences themselves are a beautiful thing, and there are lots of applications that use them. But we don't use them very much in calculus. We're focused on a different type of sequence most of the time in calculus, and they're not arithmetic. So we're not going to see these coming up very often. If they do come up, they're going to very quickly be discounted. However, let's go ahead and complete the definition just so you understand. This common difference d is the difference between every successive term. Now you have to subtract in the same order every time. So it's always the one after minus the one in front of it. So if we're looking at that sequence we had up above, starting at 5 and 8 and 11 and 14 and so on, then 8 minus 5 equals 3, and 11 minus 8 equals 3, and 14 minus 11 equals 3, which tells us that the common difference is 3. And it serves as the slope of the line in the explicit formula for the sequence. Now, if we were to plot an arithmetic sequence on the Desmos plotter, we'll see that it either goes towards infinity or towards negative infinity, like a line does, right? It either does this or it does this as x goes to infinity or as n goes to infinity. And as a consequence, they're not very interesting to us because they either blow up to infinity or they blow up to negative infinity as we move to the right. And again, we don't go to the left, right? The lowest subscript value we're ever going to use is 0, so we're going to chop it off there. So we're interested in what happens as we move to the right as n goes to infinity. In calculus, we're mostly concerned with a different type of sequence or different types of sequences. One of the main ones is called a geometric sequence. Now, a geometric sequence leads to what's called a geometric series. And geometric series are very important in the study of series. So what is a geometric sequence? Now remember that the series takes the terms of the sequence and adds them together. So if we know what a geometric sequence is, we just take out the commas and put in plus signs, and that makes it a series. So what is a geometric sequence? Every pair of successive terms, one followed by another, has a common ratio, not a common difference. You're not subtracting a sub n minus 1 from a sub n. Instead, you're dividing a sub n divided by a sub n minus 1. So you take the one after and divide by the one in front. And this is called a common ratio. right? So geometric sequences are one where every time you get the same ratio every time you divide. So let's take a look at a very simple example of a geometric sequence. So we have the geometric sequence 1, 2, 4, 8, 16, and 32, and 64, 128, and so on. You should already go, well, I know what that is. That's just powers of 2. Yes, as a matter of fact, it is powers of 2, because to get from 1 to the next, I multiply by 2 every time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And if I divide every pair of successive terms, I get a 2. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 1 after divided by 1 in front is 2, so the common ratio is 2. This is what's known as a geometric sequence. Now, they follow a certain pattern, and I'll show you later why they're called, well, I guess I can go ahead and do it now. One of the most famous geometric sequences is based on a half. So one of the sequence is based on a half. So starting with 1, and then multiplying by a half, and then multiplying by a half again, then by a half again, then by a half again, and so on. You can see that this sequence is different from the sequence below, and that this one looks like it's going to approach the value of 0 as n goes to infinity. And you're getting from one term to the next, not by multiplying by 2, but by dividing by 2. But remember that division is just a form of multiplication, so I could say I'm multiplying by 1/2. Now, where did it get the name geometric? Why geometric? Where's this coming from? Well, the idea, and this goes back hundreds, thousands of years, is to start with 1 unit square. So from here to here is 1 length long, and from here to here is 1 length long. And then you divide it in half, like this. And then you take half of the half, and you get that. And then you take half of that half, which would give me an 8, since I've now got a 4th over here. And then half of that half, and then half of that half, half of that half, half of that half. Could I keep going in this pattern forever and ever and ever? And the answer is yes, I could. Right? Well, if I do that, does this ever end? Does this sequence of numbers ever end? And the answer is no, of course not. I can always take half of the area that is remaining, and I'll still have a non-zero amount of area left. Though, then if I take out the commas and I put in plus signs, that means that I should be able to add these and come up with a finite number, because this is a finite amount of area. You know it's a finite amount of area. I told you it was 1 square unit. And what I have here is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/128, and so on. And I know what that has to add up to. It has to add up to 1 square unit. So this series, in fact, has to add up to the number 2, which, yes, that will blow your mind. Seems kind of crazy. How can this possibly be? Well, I just proved it to you. So this is where it gets the name geometric series or geometric sequence, because it has an application in geometry based on taking half of a unit square. We'll see more about these later in the next section when we study series. But for now, we're just going to deal with the basics. And a geometric sequence has a recursive formula, which is to get some arbitrary one, you want to take the 1 in front of it and multiply by r. But again, r could be a fraction like 1/2, as we saw in the geometric series up above. Or it could be a number greater than 1. Now, to get from one term to the next, you're multiplying by this common r, so they all have this explicit formula as well. A sub n is equal to the first one in the list times r to some power. What power? The nth power. Now you'll notice that I wrote this differently than it's probably written in your book, because I want to emphasize that a first may not be a sub 1. It might be a sub 0. It could even be a sub 5. Whichever number is the first in the list, then that's a first. And the formula is to take that first value and multiply by values of r one at a time to generate the next list of numbers. And this generates a general formula. So a sub n is equal to a first, r to the n. And this is the formula for a geometric sequence. It's much more difficult to mess this one up by writing a first in the formula. If we take a look at the sequence we did up above, 1, 2, 4, 8, 16, and 32, a sub first is 1. That's the first number in the sequence. And then it becomes the common ratio 2, multiplied by 2 to get from one term to the next, raised to the nth power, 1 times 2 to the n, where the a first is 1 and r is 2. You could also, of course, write this as 2 to the nth power. 2 to the nth power, that sounds like 2 to the x power. And indeed, we'll see that geometric sequences are very much like exponential functions, with the common ratio r being the base of the exponential function. Now, we know with exponential functions that we put restrictions on the base. Namely, the base has to be strictly positive and cannot be 1. Do we have the same sorts of restrictions with sequences? Now, a function, b has to be greater than 0 and not 1. Why not 1? Because it's boring. Anything to the first power is that number. So we make the base b strictly positive and not 1. Why not the negatives? Remember, that gives that splatter pattern. If you raise it to a power with a fraction and even denominator, then you're taking the root of a negative number, which isn't real, so it doesn't really make sense to allow the base to be negative. So for exponential functions, we have strictly positive bases and not 1. What about geometric sequences? Do we have the same restrictions? Well, let's take a look at some different ones, and we're going to explore this idea a little bit in just a minute. Let's practice first writing down the first terms of the sequence. So this is a very important skill that you're going to need to be able to do, which is just write down the terms of the sequence using the explicit formula. Note we start with n equal to 0, which means I take -1 to the first power, so it's -1, and 2 to the 0th power, anything to the 0th power except 0 is 1. You cannot take 0 to the 0th. So the first number in my list is going to be -1 over 1, which gives me a -1 for the first term of my sequence. And then I'm going to let n equal 1. So this is n equals 0, or term a sub 0. And then I'm going to let n equal 1. So I have -1 to the 1 plus 1, or -1 squared, which is going to make it a positive 1. And the denominator becomes 2 to the first. And that's going to give me the value 1/2, which is a sub 1. What about the third value? Then I let n equal 3. And we continue in this pattern. Now notice when oops, not 3, 2. I'm thinking ahead to the n plus 1. When I let n be 2, 2 plus 1 gives me the 3, which is what I was thinking. And then I have -1 to an odd power, which is going to make it -1, which now seems to indicate to me that the numerator is always going to alternate between -1 and 1, because when the number is odd, it's going to be negative, and when the number is even, it's going to be a positive 1. So this then becomes a -1, and then I have 2 squared, which I could leave as 2 squared, and there are advantages to writing it that way, or you could write it as -1 over 4. And that represents A2. Let's see if you can go ahead and write down what the next pattern is going to be based on what you see up above. It's going to be increasing powers of 2, and the next power of 2 would be 2 to the 3rd, which would be 8. And then I'm going to have 2 to the 4th, and the numerator should be negative, so it's going to be 16, and so forth. I think I just wanted 5, so that's 5. right? It does continue forever. Notice that the numerators are alternating and the denominators are powers of 2, including the first one. 2 to the 0th is a power of 2. It just gives you a 1, right? That behavior of the numerator, the -1 to the n+1, causes it to alternate signs. And when we have a sequence like that, we call it an alternating sequence. So the signs alternate, positive, negative, and that's going to cause it to graph above the axis, below the axis, above the axis, below the axis. So it's going to ping pong, above, below, above, below, above, below, positive, negative, and so on. Whether it starts positive or negative depends on any constant that was present in A first, and whether the subscript begins at an even or an odd integer. So it could start with a negative, it could start with a positive. Not all alternating series or sequences start with the same value. Let's take a look at this one. This is another alternating sequence. We can see that it's positive, negative, so we expect the next one to be positive. And the way we can do that is by having a -1 raised to a power, and the power will depend on the subscript. Now, finding an explicit formula means that we have to know whether we're starting at n=1 or starting at n=0. So let's try both. I'm going to start with n=0. If I start with n=0, then my explicit formula is going to start with a -1 raised to a power. My power options, well, there's many, but the most commonly used ones to get it to alternate are the nth power, the n-1 power, or the n+1 power, one of those three. So if I take -1 to the n and the first subscript is 0, -1 to the 0 will be a positive, so it starts positive, which matches what I have up there. So this seems to be okay. Now, what if I were starting with n=1? If I were starting with n=1, then that wouldn't work, because then -1 to the first would give me an odd power, and then it would be negative, which is not matching the list of numbers. So I either need to subtract 1 or add 1 to that exponent, and either version will work. If I subtract 1, it becomes n to the 0, and n to the 0 is going to give us 1. Or if I add 1, then 1 plus 1 would give me 2, which is still even, which would make it still positive. So either n-1 or n+1 would work there. And that would fix the alternating behavior. Now we've got to work on this denominator that we've got here. So when I'm looking at the denominator, do I have a pattern in the denominator? Well, it looks like I start with 5, and then I add 2 each time to get from one to the next, to the next, to the next, a common difference in denominators. Well, that looks arithmetic to me, which must mean that I've got something that's like an arithmetic sequence, but in the denominator. So the whole thing's not arithmetic, but it's sort of behaving like one. So how about if for the first one, I say 5 plus, well, I know it's going to be the common difference, and it's either going to be times n or times n-1, or maybe n+1. So let's try just n. The first time n is 0, so I don't add anything to it, and that gives me the 5, which is the first denominator. And then the second denominator would be 7, and then the third would be 9, and so forth. So this definitely works for an explicit formula for the first, starting at 0 and going to infinity. Now, if we don't start at 0, but we start at some other value, the question is, what do we need to have over here to make it still work? I want to start with 5. So whatever goes in here the first time, which is when n=1, it's got to end up with 0. Well, then that means that I probably need n-1 in there. And if I have n-1, then 1 minus 1 would give me 0 for the first, so it would start with 5. And then for a sub 2, I would have 2 minus 1, which is 1 times 2, which would give me 2 plus 5, which is 7, which would generate the second denominator. And again, this is starting with n equal 1 and going to infinity. Where you start affects the explicit formula. And you'll notice that in both cases, this one and the one we did previously, starting at 0 made the formula easier to find. We're going to see this pattern happening multiple times. So you'll see that my preference is to start at 0. Now, the next thing we want to do is we want to look at the limit of a sequence. And then we're going to come back to what we did previously with the geometric sequences. And we're going to examine whether or not those bases to the geometric sequence need to be strictly positive and not 1, as was the case for the exponential functions. But before we can do that, we need to think about the limit of the sequence, because that's going to help us to determine whether or not the base to a geometric sequence can be a negative value, right? So when we're looking at this, this is the plot of the sequence n plus 1 divided by n squared, starting with n equal 1 and going to infinity. And you can see that it is a decreasing function. It is a function, passes the vertical line test. No, it's not continuous. No, you can't take the derivative anywhere. But basically, we've got this sequence of dots here, and it looks like the sequence is approaching 0 as we go out to infinity. In other words, if I were to take the limit and say, what happens? What do the values in this sequence get super, super close to as n goes to infinity? I would say 0. And again, that's because of the explicit formula. If I were to take the limit of that formula, then I would see that this would go to 0. In other words, the limit as n goes to infinity of n plus 1 over n squared, you know, goes to 0. So I'm predicting that based on that limit, that the eventual values are close to 0. And in fact, that's what happens. And you can see it written in better writing right here. So we took the limit of a sub n, that generic formula, which is n plus 1 over n squared, and we got 0, which is the limit of our sequence. Now, when we're doing that, we basically have 4 general cases to consider. The limit goes to infinity, or the limit goes to negative infinity. That's 2. Remember that a limit, by definition, is a finite real number. So when the limit goes to infinity or negative infinity, by definition, technically, it does not exist. Now, we still write infinity or negative infinity, but infinity and negative infinity are not numbers. They're directions. And so technically, if the limit goes to one of those values, it does not exist. One possibility is that the limit goes to some finite real number, C, 5, it goes to 5, or it goes to 1, or in the case of what we saw up above, it goes to 0. 0 is a finite real number. It's a special number, but it is still a finite real number. And the last possibility is that it doesn't exist, but it doesn't go to infinity or negative infinity. Now, when might this happen? Well, it could bounce around all over the place. It could go above, below, and never settle down or approach any one particular value. In other words, we could say it oscillates. So we have a sequence of numbers and it just oscillates. And it never gets closer to one particular value. It just keeps ping-ponging above, below, and it never gets close to one value. Then we would say the limit does not exist, but not because it goes to infinity or negative infinity, it oscillates. Now let's take a look at the precise definitions from Calculus 1 and try to make it a little bit more clear mathematically what we're talking about when we take a limit of a sequence. Now, the precise definition is we say that the limit of a sub n as n goes to infinity is infinity if for every number m greater than 0, there's an integer n such that as long as the sequence value is greater than m, whenever lowercase n, the subscript, is greater than n. In other words, whatever you pick, it's going to get bigger than that, right? Now, the informal definition would be that the limit of a sub n goes to infinity if we can make that a sub n, that term of the sequence, be as large as we want for any large value of the subscript. That is, that the value of the terms in the sequence goes to infinity as n goes to infinity. That's more the hand-waving definition. And we have a similar definition of the limit of a sub n going to negative infinity. If for every number m less than 0, there's an integer n, this is a subscript value, such that the term of the sequence is less than capital N whenever n is greater than n. And that should be an m there. So I'm going to have to fix that in the notes. That should be a sub n is less than m whenever n is greater than n, right? So in other words, the limit of a sequence is going to be negative infinity if we can make the a sub n as large in absolute value, but a negative number as we want for all sufficiently large subscripts. The values of the sequence are going to negative infinity as n goes to infinity. Now, what about the third possibility, which is that we say that the limit of a sub n is equal to L if for every number epsilon greater than 0, there exists an integer n such that if a sub n is sufficiently close to L with an epsilon, then n is going to be sufficiently close to uppercase, right? And this was the definition that we got from Calculus 1, our epsilon delta definition. In other words, the limit of the sequence is going to be some finite real number L if we can always make the sequence value get closer to L for any large n. However close you want to be, I can find a subscript value that gets it that close or closer. Now, let's take a look at what this means in terms of pictures, because that means more when you're looking at a picture. We can see here in this picture that we have a sequence of dots. It's been graphed, and you can see that there is oscillating behavior as I saw up above. But unlike what I drew up above, these are oscillating in a decreasing pattern. In other words, while they're oscillating above and below this blue horizontal line L, they're getting closer to L the further out you go. And in fact, they're getting within L plus epsilon and L minus epsilon, as long as the subscript value is greater than n. So while they're oscillating in a decreasing pattern and getting closer and closer to the value of L. So we would say that probably the terms of this sequence are going to converge to the value of L. Not probably, they will, right? So here's some more terminology for you. If the limit as n goes to infinity of a sequence exists, it's a finite real number, then we say the sequence converges, right? So we say it converges. If the limit as n goes to infinity of the sequence does not exist, but goes to infinity, we say that the sequence diverges, or we may say it diverges to infinity. If the limit of the sequence doesn't exist, but goes to negative infinity, again, it diverges, and we may say it diverges to negative infinity. What happens in that fourth case when the limit of a sub n does not exist, but it doesn't approach infinity or negative infinity? Then we just say it diverges. If it's diverging due to oscillation, then we might say it diverges due to oscillation, right? But you can also just say it diverges. Okay. Let's now talk about the actual computation of a limit of a sequence. So when we look at the actual computation of it from a practical standpoint, and we want to find the limit of a sequence, we can actually think of it as a function, and we take the limit of a function that would be the same as the sequence if we had n replaced with x. And then basically we just take the limit of that. So we treat it as if it were a function. We don't typically rewrite it in terms of x, but we treat it like it's a function of n. And we just take the limit as we did in Calculus 1. So when we're looking at these, we're going to take the limit of the sequence and we're going to have the formula f of n, some function of n, and we're going to replace it. If the limit of a function with x in it would be L, then we know that the limit of the sequence with n in place of x has also got to be L. Now, this only works in one particular direction. You want to be very careful with this theorem. This theorem says if the function, continuous function replacing n with x, approaches L, then the limit of the sequence has to approach L. It does not say the reverse, though. It does not say that if the limit of the sequence is L, that the limit of the function has to be L. And in fact, we'll see one where that does not occur. So this is unidirectional only. If the limit of a function, which is continuous, is L, then the limit of the sequence, which is not continuous, is also L, right? Now, the same is also true if it goes to infinity or negative infinity. If the function goes to infinity, then the sequence goes to infinity. If the function goes to negative infinity, the sequence goes to negative infinity. Let's take a look at this. Here's an example of what I said about the converse, switching the order. Just because the sequence approaches something doesn't mean the function does. So in the graph on the left, we can see that we have a function represented by this solid blue line, which is continuous. And we have a sequence, which is the discrete blue dots, which is not continuous. And you can see that the function itself is approaching the horizontal asymptote y equal L. So the y values are approaching L, which means that the terms of the sequence also have to approach L. In other words, the sequence has to do what the function does. Over here, however, we see that in this particular problem, if we pick up the values at the integer subscripts, 1, 2, 3, 4, 5, we can see that this generates the same sequence on the right as we had on the left. And so the sequence on the right is again approaching y equal L. The terms of the sequence are approaching the value of L. But the function itself, and it is a function, it's not differentiable everywhere because it's got lots of corners, right? You can't take the derivative at a corner, pointy parts, but you can take derivatives at these line segments in between, and you can see that the function is actually zigzagging between the horizontal asymptote L and the x-axis. So the function does not converge to a particular y value. It's going to continue to oscillate between L and 0. The function does not approach L, but the sequence does. So if the function does, the sequence does, but not the other way around. The sequence might, even though the function does not. But if the function does, we're guaranteed. Now, the normal properties for limits of functions also hold for limits of sequences. So we're going to scroll through these really quickly. These are the properties for limits. We'll let a sub n and b sub n be convergent sequences. And we'll let lowercase c and uppercase a and b be real values, some constants. If the limit of the sequence a sub n as n goes to infinity is uppercase a, and the limit of the sequence as n goes to infinity of b sub n is uppercase b, then again, we can say the limit of a constant is the constant. The limit of a constant times a sequence is the constant times the limit of the sequence. If two sequences are added together, we can split the limit and make it the sum or difference of limits. Now, this is something we cannot do with derivatives or integration, but we can do it with limits. The limit of a product is the product of the limits, including the limit of sequences. And the limit of a quotient, including the limit of quotients of sequences, is the quotient of two limits, provided always thou shalt not divide by 0. We don't want the denominator one to be 0. This last one is also pretty useful. We'll see it comes up again in series and helps us out with something called the root test. The limit of a sequence raised to a power, and it's not specifying what the power is, so it could be a square root, right? The 1/2 power, is the same as taking the limit of the sequence first and then taking the value and raising it to the p power. Now, if the limit of a sub n is a, then this, of course, gives us a to the p, with the proviso that the a sub n's are all positive when the p's might have fractions in them. So we want to make sure that we're taking real values and not imaginary values. So these are the properties of limits. One of the most interesting things about sequences and their convergence, whether or not they approach some value as n goes to infinity, is that they're completely independent of the front part of the sequence. So it doesn't matter what the front part of the sequence is. If the back part of the sequence, the front part's called the head and the back part's called the tail. So the very first, however finitely many terms of the sequence is called the head. And we can ignore the head and just look at the tail. If the tail of the sequence, which is what happens when n goes to infinity, if that approaches some particular value, then we say the sequence converges. And it doesn't matter what the front part of it is at all. And so this is also going to affect a series. When you add these together, it's going to affect whether or not it converges or adds up to a finite number. It only depends on the tail, not on the head, which is kind of a wild idea. Now, this doesn't mean the first 2 or 3 terms or 5 terms. It could be the first billion terms or the first trillion terms. The convergence of the sequence does not depend on any finite number at the beginning of the sequence. It only depends on the tail. So if the beginning of the sequence doesn't match the pattern at the end, we can ignore the front and take the pattern from the end and take the limit of that to see whether or not the sequence converges. Now let's take a look at example 7. And we have the sequence quantity 5n squared plus 1 divided by e to the n. Now, I didn't specify where this one's going to start, but we'll go ahead and assume it's starting at n equal 1 and going to infinity, because I believe that's what I graphed. So when we're looking at this one right here, we can also graph this on the sequence grapher if you want to. Right there, it will take you out to a picture of it. But you can see the picture of it over here to the right. And this is something that it is dropping quickly, is it not? I mean, it is like, whoo, right? I mean, it is like down to the x-axis. I mean, it is low. I mean, this is 0.2, 0.4, 0.6, 0.8. I'm not even at 1, right? And it is low. So it gets very low very, very quickly. Now, why would it get so low so quickly? Let's take a look at this part right here. When we're looking at this part right here, what we want to do, of course, is take the limit of the explicit formula. So we're going to take the limit of a sub n, which is the formula in the middle as n goes to infinity. So the limit of a sub n becomes the limit as n goes to infinity of 5n squared plus 1 over e to the n. Now, you know, if you were to look at these, that this has an indeterminate form. Hopefully you remember L'Hopital's rule. This has the form of infinity over infinity, which of course is indeterminate. You can apply L'Hopital's rule. You can apply L'Hopital's rule 2 or 3 times. It's going to lead you eventually to 0, which you've taken my class, you know from the relative growth theorem, that all exponentials are on an order of magnitude larger than all algebraics. So you know that this exponential function e to the n is going to overpower that algebraic 5n squared plus 1, and it's going to drive it down towards 0. In other words, the limit is going to be 0. Now, if you don't trust me, or you've never heard of the relative growth theorem, then you can simply apply L'Hopital's rule a couple of times to the numerator and the denominator. And again, we're taking the derivative with respect to n, and we know that this would lead to 10n over e to the n again, and then I can take L'Hopital's rule again, since this is again infinity over infinity, and this would lead to the limit as n goes to infinity of 10 over e to the n, which is 0. which we saw in the graph below. So we've established that the limit is 0 algebraically by taking the limit, and we've also established it graphically by looking at the sequence grapher right here. We can tell that it gets low very, very quickly. And again, how quick is quickly, how fast is fast enough? Well, this is going to affect whether or not the series adds up to a finite number. It's got to get low fast in order for it to add up to a finite number when you add these terms together. And we'll make that more precise in our study of series. Now let's take a look at example number 8. When we're looking at example 8, we want to consider this sequence here and decide whether or not it converges. And if it does converge, we want to find the limit of it. So we can see that the first term is going to be alternating, but the second one is the constant plus 1/2. So remember that to find the limit, we take the limit as n goes to infinity of a sub n, which is going to be the limit as n goes to infinity of the sum of -1 to the n over n squared plus 1/2. Now we saw from the properties with numbers that we can, with limits, that we can split the sum into two limits. And so this gives us the limit as n goes to infinity of -1 to the n over n squared plus the limit as n goes to infinity of 1/2. Now the second one is the limit of a constant, which is a constant, so that just gives us 1/2. What about the first one? Well, by the properties I talked about up above, this is algebraic, and this is either 1 or -1. This is going to overpower the numerator, and it's going to drive it down towards 0. And so, again, this has the value constant over infinity, which we know is determined. It's not indeterminate, it's determined. And this is going to go towards 0. So in this particular case, we get 0 plus 1/2, which gives us 1/2, which means that I anticipate in the graph of this one that as n gets larger and larger, that the terms of the sequence get closer and closer to the value of 1/2. And let's take a look at what it does here. Now, because of the -1 to the n that was in the first term of the explicit formula, you'll see that it's actually oscillating, not above and below the x-axis, but above and below the horizontal asymptote y equal 0.5 or y equal 1/2. And you can tell that it is oscillating, but in a decreasing pattern. As n gets larger and larger, it gets closer and closer, y equal 1/2. In some ways, I think of this like the kudzu vine out in the southeastern United States. It just chokes the life out of a tree, right? It wraps up the tree and squeezes tighter and tighter until it becomes a single point, which is 1/2. Now let's take a look at another example. And you can see here, this is the graph y equal 1/2 in red. It's kind of a close-up of what's happening there, getting close to it. Let's look at example 9. We have the sequence of the square root of quantity 2n plus 1 over 3n plus 5. We want to know, does it converge? If it converges, what's the limit? And again, converges means, do the terms of the sequence get close to some finite real value? And if so, what is that finite real value? Now, limit doesn't mean they ever become that finite real value. They just get close to it. Is it possible that they become it? Well, yeah, there are sequences that do that, but we won't study those too often. In this case, our a sub n is this expression here. We could start with n equals 0. We could start with n equal 1. I believe when I graphed it, I did n equal 1. So we'll start there again. But again, where this one starts just changes the first term in the sequence. And so now we're going to take the limit of a sub n as n goes to infinity, which is going to be the limit as n goes to infinity of that radical. Now remember that there was a property that said as long as I don't have division by 0, and as long as I have a power, I can pull the limit inside the power. Limits are so powerful. You can do almost anything with a limit. Limits are, they are truly the most powerful of all the constructs in calculus. Between the limit, the derivative, and the integral, the limit is the one that is the most versatile. and is really the foundation of calculus. Limits are everything, right? Okay, so in other words, I can pull the limit under the square root. Well, I can also pull the limit into the numerator and the limit into the denominator, or I can just look at this and I can do either L'Hopital's rule. This has form infinity over infinity. Taking the derivatives, I would get 2/3, or I can use that relative growth theorem that says this is degree 1 and that's degree 1, and the ratio of the leading coefficients is 2/3, and so it's going to approach 2/3. Whichever way you want to compute that, you should end up with the square root of 2/3, which means that in this sequence, as n gets larger and larger, the terms of the sequence get closer and closer to the value square root of 2/3. And if we look at the graph down here, you can see that that's exactly what happens. This one is what I would call a strictly increasing function. Notice how it's only going up. It's not oscillating up and down. It's not decreasing. It's going up in value. The y values are increasing, but they're getting very, very close, closer and closer, the further out we go, to the square root of 2/3. Now we want to talk a little bit about the Squeeze theorem for sequences. We've seen the Squeeze theorem with functions when we did limits. We want to look at the Squeeze theorem for sequences, which is in essence exactly the same as it was before, but with sequences instead of functions. So, but in a sense, a sequence is a function. It's just a bunch of discrete points instead of a continuous graph. So if we have a sequence B sub n, and all the terms of the sequence are between A sub n and C sub n for at least the tail. Notice this n greater than capital N. This basically means for the tail of the sequence. Now, it may mean that that doesn't hold for the first 10 trillion terms, and that's okay. But after the first 10 trillion terms, it's always the case from there on out that B sub n is between A sub n and C sub n. Then I can use the Squeeze theorem. Now, the Squeeze theorem says the limit of the term on the left, the low end, and the limit of the term on the right, the high end, both go to L. Then the limit of the sequence in the middle also has to go to L. This is you on the freeway, and you have a car in the lane on your right and a car in the lane on your left, and they're right next to you, and the road splits and they decide to go to the right, you're going to have to go to the right in order to not have a wreck. You have to go where they go and do what they do. They go to the left, so you have to go to the left. I think I actually went to the right there, didn't I? Okay, so essentially it's the same as it is for functions. And again, the head of the sequence, the first finite number of terms, does not affect the convergence. It's only the tail. So it only has to be true for the tail. Now, we use the Squeeze theorem most often for sequences that we can't directly take the limit of. This can happen frequently with alternating sign sequences. It's also useful for sine and cosine. And we have a picture right here of one that's alternating. And the alternating one is B sub n, which is the black dots. And you can see that all the black dots are below all the blue dots. So they're below all the C sub n. So B sub n is less than equal to C sub n for all values of the subscript. And you'll also notice that the black dots are all above the red dots, which is A sub n. So B sub n is squeezed between C sub n and A sub n. It's between the two. But C sub n is what I'd call a decreasing sequence because the values are coming down and they're approaching the horizontal asymptote y equal L. And A sub n, the red dots, are what I'd call an increasing sequence because it's coming up and again approaching the horizontal asymptote y equal L. And since B is between, it's got to approach L as well. It doesn't have a choice. It's in between A sub n and B sub n, or C sub n. Let's take a look at how to apply that with this particular sequence that we have here. This is the limit as n goes to infinity of the sequence 2n minus sine of n all over n. Now, when we're looking at this particular one, what do we want to do? I mean, what are some of the values that we can think about, or how we want to split this up? When you're looking at using the squeeze theorem, what you typically want to do is you want to try to build what's in the formula by starting with, in this case, the trig function. So I'm going to start with sine of n. So I'm starting with sine of n. And I know that sine, by definition, has to be between 1 and negative 1. Right? So I have sine between negative 1 and 1. Now, the next thing I notice is that in my explicit formula, it's not sine of n, but negative sine of n. So the next thing I want to do is I want to multiply through by a negative. Now, when you multiply or divide by a negative in an inequality, this is going to reverse the symbols. So these guys get turned around, and I have a negative 1 times sine of n. And this is going to get turned around, and I have a negative 1 times 1. So I get 1 greater than equal to negative sine of n greater than equal to negative 1. Because I multiplied by a negative, I reverse the sense of the inequality. I reverse those inequality symbols. Now I'm trying to build what I have in the explicit formula, so I want to add to n. Now remember, n starts probably at either 0 or 1 and goes to infinity. Well, it can't start at 0 because that would be undefined, so we'll start it at 1 and go to infinity. So 2n would be strictly positive, but it shouldn't matter anyway, because if I'm adding it to all three parts of the inequality, adding does not change the sense of the inequality. So I'm going to add 2n to all three parts. So I have 2n plus 1 greater than equal to 2n minus sine of n greater than equal to 2n minus 1. So I just basically added 2n to all three parts of the inequality. Now, the next thing I want to do is I want to divide by n. I have to be careful when I divide by n. First, I have to make sure that it's not division by 0, and I can make sure that that happens by making sure that n goes from 1 to infinity, or from some larger value to infinity. The other thing is I have to think about whether n is positive or negative. Now, we know from the definition of sequences that n is never negative. We don't use negative values for subscript values, so we know it's strictly positive. That's important because if it were negative, it might reverse the sense of the inequality. So then I divide all three parts by n. And this gives me two functions. I have one on the left here highlighted in blue, and one on the right highlighted here in pink. And my particular sequence, 2n minus sine of n all divided by n, is between those two. And so then what I can do is I can take the limit of the sequence on the left and the limit of the sequence on the right and see if they approach the same value. So the limit of the left sequence as n goes to infinity of 2n plus 1, oops, getting ahead of myself, 2n plus 1 over n. Well, again, I have the same degree numerator and denominator, so I'm going to get the ratio of the leading coefficients, or you can apply L'Hopital's rule. It has form infinity over infinity, and that brings us to the limit value of 2. And that's the limit on the left. So this is the left sequence. And now we want to take a look at the right sequence, the one that is highlighted in pink. And if I were to take the limit of that sequence as n goes to infinity of 2n minus 1 over n, notice that because of the nature of that formula, I still get 2, which means that the limit of the sequence on the far left and the limit of the sequence on the far right are the same. Therefore, by the squeeze theorem, the limit of the sequence in the middle must also go to 2. And that's what we would write in words. Therefore, by the squeeze theorem, the limit as n goes to infinity of 2n minus sine of n over n is also equal to 2. It has to go to the same place as the 2 on either side. Right. Now let's take a look at the next theorem that we have here. We have a little bit more to do, and then we're going to take a break and we'll do the rest of it in another video. But we have a little bit more we want to talk about. One of the reasons we were talking about all this is we wanted to decide about convergent or geometric sequences, whether or not the base of a geometric sequence, that common ratio r, did it need to be strictly positive and not 1, like the exponential functions? They look so much like exponentials. Are they like exponentials? We have this theorem right here, which can be proved using the Squeeze Theorem. I'm not going to go through the proof. We don't use this one terribly often, but it does come up when we talk about the geometric sequences, so I do want to include it. It basically says if the limit of the absolute value of a sequence goes to 0, then the limit of the sequence without the absolute value must also go to 0. Now, the 0 here is important. It will not work for any other value. It will only work for 0. If the limit of the absolute value goes to 0, in other words, whatever the terms of the sequence are, you make them all strictly non-negative. And if, as you go to infinity, those values get close to 0, then it must be that if you allow them to be positive or negative, that it still goes towards 0, right? Even if it were alternating in sign. Now, this only works for 0. And this is equivalent to saying, of course, that if the limit of the sequence does not go to 0, then the limit of the absolute value of the sequence also can't be 0, right? If the limit of the sequence goes to 5, then the limit of the absolute value can't be going to 0, right? So let's reconsider our geometric sequences. One of the things we were wondering about was we've got this common ratio r raised to the n. Now, this is basically a geometric sequence. Now, the normal form for a geometric sequence is a first r to the n. So we have some constant being multiplied by r to the nth power. And this r to the n looks like an exponential function. So our question was, does the base need to be strictly positive and not 1? Or can we allow negatives? What would happen if we did this? So we want to think about these in terms of different ones. And so to start, we're going to look at exponential functions where the base is greater than 1 or where the base is between 0 and 1. So this second case right here is actually between 0 and 1. So we're considering these two cases at first. These are the ones that match the exponential function, r being strictly positive, either greater than 1 or between 0 and 1. Remember, there are a lot of numbers between 0 and 1. All right, you can't just say greater than 1 because then you're leaving out 1/2, 1/3, 4/5, and so on. An exponential function where r is greater than 1 is going to look like this. It has exponential growth. So as n goes to infinity, we would predict that this one is going to go to infinity, which means that the limit of the sequence would diverge to infinity. What about this one, where the common ratio is between 0 and 1? Well, this is similar to an exponential function with decreasing behavior. This would be exponential decay. And as n goes to infinity, it approaches 0. So we would say that the sequence then would have to converge, right? So we're predicting that the sequence would converge in that case. So we would not be as interested in the one on the left because the sequence would diverge. The function diverges, therefore the sequence diverges. So we're not so interested in that one. We would be interested in this one where the sequence is going to converge. The function converges towards 0, so the sequence is going to converge. So that one is interesting to us. Now let's take a look at allowing r to be negative. So we've taken care of everything except 1 and the negatives. Well, and 0, but we wouldn't raise 0 to a power because we just get 0. So that wouldn't be very interesting. And you'll see that 1 doesn't result in anything super interesting either, but we are going to look at it as a separate case. So now let's think about negative values for R. Can I let them be different negative values? We're first going to divide this into 2 regions. So what we're doing is we're looking at the real number line and we're dividing it into regions. And we've looked at this and we've said that it converges in here and it diverges out here. Now we want to consider the values that are below -1. So these are the ones where R is less than -1. So this would be -2, -3, -4 out here to the left. If this is the common ratio, it could be a fraction as well, right? There's nothing to say R can't be a fraction. And in fact, it can be. Well, let's look at what happens if we take an example of this and we plot it on one of the sequence plotters. So this is -2 to the n. So we're looking here at the plot of the sequence a sub n equal to -2 to the n. And this is from n equal 1 to infinity. So we're looking at that graph right here. What happens? Well, you can see that it starts out close to the x-axis and it alternates because of the negative raised to the nth power. But then as it gets further out, the values get larger and larger and larger. So they start going towards infinity, right? And if we were to do this on the graph and we push further out, we see they get even further apart. So that means that as n goes to infinity, they start oscillating bigger and bigger and bigger. The oscillation grows larger and larger and larger, which means that the sequence is not going to converge to any particular value. So in that case, the limit does not exist, and we would say that it diverges in this region as well. Now, we want to know what happens in here between -1 and 0. What happens in that region? So we can take a similar plot, and this time we're looking at -1/2 raised to the n. And we can see that in contrast, this one, they start further away from the x-axis, but as n goes to infinity, they are still oscillating above and below because of the negative on the base, which is R, but they get closer and closer to some particular value. In fact, in this case, they get closer and closer to 0, so it converges towards 0. So we can see that this one gets very low, very quick, and even though it oscillates positive, negative, it does converge. So now we want to know what happens at -1, at 0, and at 1. Well, we can discount 0 right away, because if we let R be 0, then 0 to any finite power is 0. So it just graphs as the horizontal line, which becomes 0, which is not terribly interesting. It does converge to 0, but it's not terribly interesting. Let's take a look then at -1 and 1. What happens when R is 1 to the n? So when we look at the graph of 1 to the n, well, obviously 1 to a finite power is just 1. And so you get a sequence of dots at 1. Now, obviously, it converges to 1, which is not terribly interesting. It's sort of like 0. It's not terribly interesting. What happens when it's -1 raised to the n? So we've got the sequence -1 raised to the n, starting with n equal 1 to infinity. Well, because of the negative, they're going to oscillate. So they're going to be negative and positive, and so on. So they're going to oscillate between 1 and -1, or -1 and 1. Well, that's a problem, because as they oscillate, they're not dampening. They're not decreasing oscillation. The oscillation is staying exactly the same. It's always oscillating between -1 and 1, which means that as n goes to infinity, the values of this sequence do not approach 1 or -1. In fact, we see that the odd ones go to -1 and the even ones go to 1. And since the odds and evens go to different values, then the limit of the sequence does not exist. So we can see that at -1, it doesn't exist. It diverges. And at 1, it converges. So what have we gained so far? If we think about a sequence R to the n, where I'm letting A first be 1, we know that it will converge if R is between -1, not equal r, and less than or equal to 1. And it diverges for everything else except 0, but we don't want to let r be 0 because then it's just the graph of 0, which is kind of boring. So it diverges for everything else. So when we're looking at this, it's not only that it converges, they all converge to 0. So the limit of r to the n actually approaches 0 if r is between -1 and 1 strict inequality. If I take off the equality equal to 1, then it doesn't go to 1 anymore. They all converge to 0. So again, we're looking at these graphs right here where they're oscillating down to 0, right? Coming down towards 0. Now let's take a look at this representation of what's happening. This basically means that the limit of r to the n is 0 if r is between -1 and 1, and it's 1 if r equals 1. Well, when we talk about adding up the terms of the sequence, and the sequence being infinitely long, if we add 1 to itself infinite number of times, we know that's going to blow up to infinity, so we're not so interested in that. But we are interested in these guys. Because the values get very low very quickly, it's possible that they'll add up to a finite number, and that's what a geometric series is. And that's where we're really interested in going, which is into series, the sum of the terms of a sequence. This is also an example of why the theorem up above, that the limit of the absolute value of a sequence going to 0 means the limit of the sequence going to 0 only works for 0. Because if a sub n is -1 to the n, then the absolute value of it would be 1 to the n, and the limit of that goes to 1. But we just saw that the limit of -1 to the n oscillates between -1 and 1 and diverges. So this theorem only works when the number on the other side is 0. It doesn't work for any value other than 0. Now we want to talk about a couple more ways of determining whether or not a sequence converges or diverges. And we saw this just a minute ago. This is especially good for alternating sequences, which is to divide it into the even terms alone and the odd terms alone to determine whether or not it converges. And again, we only have to pay attention to the tail. So if the beginning of the sequence doesn't follow the pattern, you can chop it off and set it aside. It will affect the series, the sum of all of them, but it won't affect the convergence of the sequence, which only depends on the tail. If we look at just the odd subscripts and they approach some particular value and the even subscripts approach the same value, then we know that the sequence itself must approach that value. However, if they go to different values, then the limit of the sequence does not approach a particular value, right? So here are the different possibilities. Either they have the same limit in which the limit of the original sequence is that value, or they both go to infinity, so the sequence does, or they both go to -infinity, so the sequence does, or they have different limits, either infinity, -infinity, or some finite value. But if they're different, then the limit of the sequence diverges and does not exist. And that's basically the rules for what we have for the convergence of a sequence. Now, the next thing that we want to talk about will be in the next video, which is going to deal with bounded and monotonic. It's a very short section, but this video is already long enough. So I'm going to stop here and we'll talk about bounded and monotonic sequences in the next video.